Hi everyone and welcome back. In this lesson 1.2, we're going to look at displaying and describing the distribution of quantitative data. So in the last lesson, we looked at how to display distributions of categorical data. And if you'll recall, we used bar charts. You can also use pie charts, segmented bar charts, also Pareto bar charts. So when we're dealing with quantitative data, however, we cannot use those displays. We have our own set of displays. When we're dealing with quantitative data, one of the other things that we need to figure out is we need to create partitions within our distribution to be able to separate the data. When you have categorical variables, the categories form natural groupings. So it's really easy to make up the bars in a bar chart because they just naturally form their own groupings, right? If you have a pack of Skittles, you count the number of red Skittles, right? So red is a category. It's automatically grouped. But let's say I have a bunch of data that's quantitative. Maybe it could be temperatures for a month or a year. How do I group those? You could group it monthly, then that would mean you're looking at the data categorically. But let's say I don't want to look at it categorically. Let's say I want to, find average temperatures or the median temperature of a year. Then I'm looking at quantitative data and I need to construct a different type of graph. And we need to partition the data into what we call bins. So a bin is just an interval that groups together a range of different data values. So there's an activity that you'll complete in class. It's called How Long is a Minute? But we can't do that here online. So I'm going to just give you a set of data, and we're going to create a table and then create a histogram, which is a type of display we use for quantitative data. Okay. When we are looking at these graphs, we want to try to find patterns within the data set. So in order to find those patterns, we need to group the data values into bins, right? But those bins have to be equal width. I can't have one bin, represent 10 different numbers or a range of 10 numbers, and then another bin represent only a range of 3 numbers. So I need to figure out the bin width, right? And I need to make all of the bins the same width. If the bins are too wide, you end up with, if the bin widths are too wide, rather, you end up with skyscrapers because eventually you'll end up dumping a ton of data values into that bin. And if the bins are too not too wide, if they're narrow, you end up with pancakes or a flattened graph because you can't fit many data points into that bin. So we have kind of a unwritten rule where you want to have a histogram that produces anywhere from 5 to 15 bins or bars, okay? So that's usually a reasonable choice, all right? So let's just take a couple data points, okay? And we're going to look at how to construct a histogram. So for example, let's say my data was the following, okay? So we'll call this sample data. And this will just give you a general idea of, how to construct a histogram, okay? So we've got 22, 23, 25, 15, 18, 20, let's do 27, 19, 11, 21, 21, 21, 30, 30, 24 and 18, 24 and 25. Okay. So I need to figure out how wide to make the bins. So this is what I'm going to do. I'm going to first find the range. Okay, so to find the range, you're going to take the highest value or your maximum value, which is 30, and we're going to subtract the minimum or your lowest value. So 30 minus 11. Okay, so my max is 30. My min is 11. And to find the range, I'm just going to do max minus min. 30 minus 11 gives me 19. Okay. You're always going to add 1 to it. So you get 20. And let's say I want to have 5 bars. So I'm just going to divide by 5. And I get this number 4. Okay, what does 4 represent? So when I start to create my table, my bin is going to start at my min, okay? And you know it's going to end up at your max. So that number 4 means I'm going to take my lowest number and I'm going to add 4 to it to get my next bin. So 11 plus 4 gives me 15. So that tells me my first bin is going to go from 11 to 14, okay? And then my next bin is going to go from 15 to 18 because 15 plus 4 gives me 19. So I'm always going to keep adding 4 each time, okay? So 19 plus 4, 23, 23 plus 4, 27, okay? And so on. So I'm not going to go all the way down to 30 there. The 30 will actually stop there. So this is going to be 19 to 22, and then this is 23 to 26, and then that's just 27 to 30. Okay, now I'm going to count. Okay, tally means to count, and we use tally marks. Tally marks are these like vertical bars, okay, which represent 1. When you have a group of them with a slash through it, that usually represents 5. Okay, so it's easy to count the tallies. So what I would go through is, okay, how many numbers, how many data points do I have that go from 11 to 14, right? So if I come back up here and now I figure this out, I've got, and I can just circle them, 11 to 14, I've got one number there, and it looks like that's it for the 11 to 14 group. So you would have one tally mark, and frequency, remember, just means counts. So if I count the tally marks, there's just one tally mark there. Okay, for 15 to 18, now I'm going to go through and count anywhere that's a 15 to an 18. So I see 1, 2, 3. Okay, so I'm going to put a 3 here. There's 3 marks, and the frequency would be 3. I'm going to do the same thing for 19 to 22. So there's 1, 2, 3, 4, 5, 6. Okay, so I would do 1, 2, 3, 4, and then 5, put a bar through it, and then 6. And then 23 to 26. So 1, 2, 3, 4, 5. And then 27 to 30 should be my leftovers. So I have 1, 2, 3. And that's all there is to making a frequency table with tally marks. Okay, we also know that as a frequency distribution table because it's showing you the intervals and then the counts within each interval. So if you'll recall, the distribution of a variable gives the possible values of the variable and how often the variable takes on each of those values. So these are your possible values, they're your intervals, and then that's how many times each of those values occurs. Okay, that's one way to show the distribution of a variable. Notice that each of each row contains equal size bins. So each of these is known as a bin. Okay, and my bins are about 3 units long. 4 units really. So 11, 12, 13, 14, and then 15, 16, 17, 18, and so on. And the sum of the frequencies always equals the number of values in the data set. So if I add these up, I get 8 plus 6, which is 14, plus 4 is 18, and I should have 18 numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 2 is 18. Okay, so right here my bin width, again, was my bin widths are 3, 14 minus 11, 18 minus 15, and so on. Okay. So we can take the frequency table and we can display it using a histogram. A histogram is a type of graph that is used for quantitative data. Okay, it's very similar to a bar graph, except that it's not. You've got your bins, right? And the height of the bar is the frequency of the bin. And then we draw bars for each bin on the graph, okay? Histograms don't have spaces between the bars, unlike bar charts, which can. The only time there would be a space in between the bars in a histogram is if there just naturally occurs 0 numbers in that interval. And as you can see in our frequency table, we don't have any zeros. So all of our bars in the histogram are going to be together. Okay. Now, when you look at your this histogram here, notice that we have the words who and what. Okay. So the what is going to be your horizontal axis, and then the who are the frequency and the vertical axis. Okay. So now we know that we started our bar at 11. So there's like a gap here, and usually you can put like a little jagged line to show that it goes from 0 to whatever number you're starting with. Okay, so there's a space in the graph. And then what I'm going to do is I'm going to label it using these numbers here. So 11, 15, 19, 23, and 27. Okay, so 11, 15, 19, 23, 27, and we know it ends at it would actually be 31, right? Okay. So this is saying basically everything including 11 but not including 15 is going to go in this bin, and anything including 15 but not including 19 will go in that bin, okay, and so on. So as you can see here, my first bin, I should only have the bar go up to a 1. In the second bin, it goes up to 3. In the third bin, it goes up to 6. In the fourth bin, it goes up to 5. And then we have 3 again. And that's your histogram. Okay. We can also create what's called a relative frequency, and that's when the bins represent the proportion or percentage of the data values that are contained in the bin. So if I wanted to convert this frequency table to a relative frequency table, I would need to know the sum there, right, which we said is 18, so your total is 18, and you would divide each of those frequencies by 18. So if I was to create another table here and add an extra column, my relative frequency would be 1 divided by 18, and I don't know what that is, but we can figure that out using Desmos. So 1 divided by 18 gives me 0.05 repeating. So to convert that to a percentage, I just need to move the decimal place 2 to the right, which is just multiplying by 100. So this is like 5.6%, and so on. So you would do 3 divided by 18, 6 divided by 18, 5 divided by 18, and 3 divided by 18, and convert them to percentages. And the percents are your relative frequencies. So you can also create relative frequency histograms as well. Okay, so we made a picture. Now we want to know, like, what can I pull out of that graph? Okay, so one of the things that you can pull out of there is the center of the data. Okay, the center is viewed as the typical value that could be used to represent the data, right? So if I was looking at this graph here, right, I would try to find like a balance point. The balance point would be like my average maybe, which eventually we'll learn is a measure of center. So it's a typical value. And I would say that it would fall somewhere between 19 and 23, okay? And I know that because I had 18 data points, so half of 18 is 9. And if I count, I have 1 plus 3, which is 4, plus 6 is 10. So I'll automatically have 10 data points here. So the average is somewhere between 19 and 23, right? So you figure it's about 21 would be the average or the center here, okay? So to me, it would be 21, okay, is the most common length of time perceived here. And again, this data is made up, okay? So 21, and it's more like the balance point, okay? If you were to balance that graph with your finger, it would be about 21 right in the center there. Another way that we can describe data is using what's called the spread, and that's the distance from the lowest value to the highest value. And we saw that when we were creating the bins. So the data went from 11 to 30, okay? So the lowest was 11 and the highest was 30. So that would be my spread, the data spread, a range from 11 to 30, okay? Now, are there any potential outliers? So if there's any gaps in the histogram, that could be an indication that there's an outlier. There's actually a mathematical way that we can figure out outliers, but we will learn that in section 1.4. So we're not ready for that right now. But as you can see from the histogram, there really are no gaps. There's no numbers that extreme values that are away from the rest of the other values. So there's really no apparent outliers. Okay, an outlier is just an outsider. It's an extreme value away from the highest and lowest values. Okay, but there don't appear to be any outliers. Okay. And the third thing that we can look at when we're looking at a distribution is we can look at the shape, okay? And shapes describe the patterns we see in the data. So here's some common shapes. We've got skewed distributions up top here. So this distribution on the left, this histogram is skewed to the left. And the way you can tell is pretend it's a whale and just draw the tail, right? The tail is right here on the left side. That's where the data kind of trails off, so it's skewed to the left. Whereas the histogram opposite it is skewed to the right because the tail is on the right. Underneath that, we have a uniform distribution. So the word uniform means the same. All of the bins are the same height. Now, I want to caution you, though, in the real world, this would never look like this. Okay, when you're dealing with real life data, it's never going to be exactly uniform, but the bars could be pretty close together, which would look like it's kind of flat. And then the fourth type is a bell-shaped distribution. It's also symmetric, so if we fold it down the center, both sides are equal. Again, you're dealing with a textbook perfect picture. In the real world, the normal or bell-shaped distribution doesn't look perfect on both sides. It will represent a bell, but it may not be a perfect bell, okay? We will look at the bell-shaped distribution. It's a very important distribution in statistics later on. And what you want to remember is that this is also known as the normal model. And in statistics, we work with problems that are normally distributed. So you will see that again in the future. So what I need to do now is I need to take my center, my spread, and my shape and put it all together in a paragraph. So what you would need to do is write a brief paragraph describing the distribution by talking about the center, spread, shape, and any outliers in the distribution. So anytime you are asked to describe the distribution, you're going to always mention these 3 to 4 things. You're going to mention center, spread, and shape, and then you're going to mention outliers if there are any, and that's really important, okay? So the activity in class is all about, the activity is called How Long is a Minute? So when you're writing your paragraph, you want it to be in context. Here, there's no context for our data. They were just 18 numbers that I came up with to give you an idea of how to make a histogram. But basically, what you would want to say, if you go back, is let's pretend these were how many seconds people thought was a minute. Okay, so generally the way the activity goes is you have a partner and the partner will tell you, you start counting, and the partner will tell you when to stop counting after they think a minute has passed, right? So let's pretend here this 21 would represent that the average time that elapsed before someone thought a minute passed was about 21 seconds. Okay, the number of seconds that the range of the number of seconds that people thought was a minute spread from 11 seconds to 30 seconds. And the distribution appears to be, if you said bell-shaped, that would be pretty bell-shaped, right? And we would also call it unimodal. So when we get to measures of center, we'll talk more about the mode. The mode is the data value that occurs the most, and it's usually wherever the peak is. And here the peak is just this tall bin right there in the histogram. So if you were to compare the shape of that histogram to the 4 shapes here, you would say that it resembles mostly the bell-shaped distribution. Okay, and then there don't appear to be any outliers. So if there's no outliers, you don't even have to mention it in your description. I would just ignore it. If there were outliers, then that's something that you would want to mention. Outliers don't mean that there's something wrong. They're just extreme values. Sometimes they represent one of the most interesting data points. Like, why is that outlier there? It sometimes is important. Okay, so some things that are important that we talked about: frequency distribution of a variable. It's a table or graph containing all the values of the variable and how often that variable takes on each value. And then from that table, we created a histogram, which is just one type of graph we can use for quantitative data. And from that histogram, we looked at the center, the shape, and the spread. Okay, so the center is the typical value for right now that best describes the distribution. We actually will look at specific concrete values for center, and there's appropriate and inappropriate times to use certain centers, so we'll talk about that. The shape of the distribution is a description of the overall pattern, so you've got skewed right and left, uniform, and bell-shaped, which we also know as normal. And then the spread is a description or measure of how much the data values vary or change around the center. So how spread out, from what value to what value. Again, we're going to get very specific and mention concrete values that will quantify that word spread. Okay. And as I mentioned earlier, another important characteristic to note about a histogram is whether it has a single or central hump or separated humps, and those are called modes. The mode is the number that occurs the most. When a histogram has one hump, as the one we did has, it's called unimodal. So the prefix uni means one. Histograms with two humps are called bimodal, right? Bi means two. Three or more we just call multimodal. Okay, so here's an example of unimodal. The mode is right here in the center. It's where the peak is. And then we've got two modes here. We have a mode there, and we also have a mode there. Okay, and the mode is the number that occurs the most. So this would be your unimodal distribution, and this is the bimodal distribution. You also want to make sure you identify any gaps in the distribution. So if there's any spaces, it can encourage us to notice when data can contain more than one group. So, here, if there was a space here, that would be something important. Like, why did the data just all of a sudden split into two groups? There might be something interesting about that. Another type of graph that we can use for displaying quantitative data is called a stem and leaf plot. Stem and leaf plots are easy to look at. They're kind of tedious to make when you have a large data set. So sometimes they're not realistic. But what's nice about them, so if you want to call it an advantage is you can actually see the values. Whereas if you think about it, when you look at a histogram, we don't know what values are in here just by looking at this. Are there a bunch of 19s? Or is it 19, 20, 21, 22? We don't know, okay? So, histograms are easier to make, especially when we have large data sets, but we can't see the values, they're hidden. In stem and leaf plots, we can see the values. So a stem and leaf plot is created using a number, stem, and leaf. So if you take the number 68, for instance, the number 6 is called the stem, and the 8 is called the leaf. So hence the name stem and leaf. These represent pulse rates, right? So again, it's always important to label your graph or your table so that we know, what we're looking at here. So I look at this and I'm like, oh, these are pulse rates. So the way you read this would be 68, 68, 68, 69. And the key here tells me how to read it. It says 6 vertical bar, which is this, and then 8 means pulse rate of 68. So by looking at this, I can see that I have pulse rates ranging from 68 to 110, okay? One of the other cool things is that if you take a histogram, and so let me copy it and then paste, okay? If I turn this on its side, you now have a histogram. So I can look at this and I can see, if you were to describe the shape, to me, this looks like it's skewed to the right. So the distribution of pulse rates appears to be skewed to the right, okay? The center appears to be somewhere in here. So that would tell me the typical pulse rate of people would be around 70 beats per minute, 74 beats per minute. And the pulse rates range from 68 to 110 beats per minute, okay? You can practice making a stem and leaf plot of our minute data. And then it's important to go through a summary of what we talked about here. And please make sure you take the time to complete the homework as well. So if you have any questions, feel free to reach out to me. I'm happy to help. Please take the time to do the homework, because anything in the homework could be on the weekly quiz. All right, have a great day, everyone.